Hello, welcome to the fifth lecture on cosmology. So, till now we have been studying the smooth universe. This is based on the fact that our universe is homogeneous and isotropic when smoothed over large scales. However, if we want to explain the structures around us like the galaxies, the clusters of galaxies and so on, we need to somehow incorporate inhomogeneities as perturbations on top of this smooth cosmological background. Formalism becomes much simpler if the amplitude of these perturbations is small. In that case, we can use the linear perturbation theory and work out the mathematics relatively easily. This, for example, will hold for the universe during the time CMBR was generated, because we have seen in the last lecture that the CMBR anisotropies have fractional amplitudes of the order of 10 to the power minus 5. These are small, so we can deal with such perturbations using linear theory. Just to refresh our memory, the background metric, which is valid for a smooth, homogeneous and isotropic universe, is given by the FLRW line element, which I have written here. ds square is c square dt square, the time part, and then the scale factor square times the spatial part of the metric. Now, the full theory of perturbations, even in the linear limit, is actually quite involved. It is mathematically quite involved. There are a lot of subtleties. So, it is not possible to cover all such aspects in a small lecture course like this. So, rather in this lecture we will discuss only the main features, and that too keeping the framework as simple as we can. Our main aim would be to try to explain the inhomogeneities or anisotropies we observe in the CMBR sky. We will also make things a bit simpler and work in units where c is equal to 1. So, for example, the c in front of dt will vanish from now on. We can always put it back whenever it is needed. A very useful time coordinate for studying perturbations is the so called conformal time. So, the conformal time eta is related to the conventional cosmological time t by a relation like this. So, d of eta is just dt over the scale factor at. Now, if I want to write the metric in terms of the conformal time, what happens is this: the metric is a square, which now has become a function of eta, times d eta square minus dl square, the spatial part. So, you can see it has taken a somewhat different form, in the sense the a square is sitting in front of the rest of the metric. Many things simplify in this metric. For example, in this case the radial light rays will follow the trajectory given by d eta equal to plus minus d chi, where remember chi was the radial coordinate which we have been working with so far. So, in this sense the conformal time is a direct measure of radial distance to an object, a galaxy or whatever you can think of. Some of the expressions for various parameters would change. For example, the Hubble parameter, when written in terms of the conformal time, picks up an extra factor of a. The Hubble parameter in conventional time coordinates is a dot divided by a. In terms of the conformal time, the Hubble parameter is a prime by a square, where by prime I mean derivatives with respect to eta. So, whenever we write dot, it will be a derivative with respect to the conventional time coordinate t, prime would denote the derivative with respect to the conformal time. So, you can already see h is not A prime by A simply, but it is A prime by A square. This extra factor of A comes because of the extra factor of A in the definition of the conformal time. Okay. Now, if we want to study perturbations, basically this involves writing the metric GIK as GIK bar, which is the metric for the smooth universe, say the FLRW metric, plus a small quantity delta GIK, which denote the perturbations on top of the smooth metric. Similarly, one should also write the stress energy tensor as a smooth part, which we have already talked about while doing Friedman equations, plus a perturbed part, okay, which we have denoted by delta of TIK. Now, once you write the metric like this, what you can do is you can then solve the Einstein's equation and get the solution for the perturbations. This is the broad idea, but as I said earlier, doing this is not easy. There are many subtleties involved in terms of coordinate transformation and so on, and we will not try to go into all those. If the perturbations are small, let me repeat again, it is sufficient to work just in the linear limit. Now, if we are interested only in scalar perturbations, like the perturbations in density, pressure and so on, scalar quantities, it turns out we can write the metric simply as like this. So, ds square is the a square eta, which comes out as we have seen, and then in the coefficient of d eta square, it picks up a term which is written as 2 psi. Similarly, the coefficient of the spatial part picks up a term which I have written as 2 phi. So, the metric becomes something like this, where remember psi and phi are the gravitational potentials, and in general they depend both on the time coordinate, it can be t or eta, and also the spatial coordinates. There in general there could be other kind of perturbations as well. For example, there could be tensor perturbations which would correspond to gravitational waves, but for the moment we will keep our discussion simple and we will talk only about scalar perturbations. The advantage of working in linear perturbation theory is that the equations for scalar, vector and tensor perturbations actually separate out. So, when you want to study only scalar perturbations, it is sufficient to write the equations for scalar perturbations, because they will not couple in any way to the tensor perturbations and vice versa. The calculation simplifies further when there are no anisotropic stress. So, in that case these two potentials become equal to each other, and then it is just sufficient to work with one potential, either psi or phi, whatever you call it. Now, suppose we take a model where the universe is filled with just one fluid, okay, or in other words, if the universe is dominated, the energy density is dominated by just one kind of fluid, which has a equation of state like this, P equal to W rho, then what happens is you can work out the Einstein's equation, which essentially would be an equation, differential equation for phi, for example, and that would look like this. There is a phi double derivative term, there is a first derivative term phi prime, and then there are terms which are proportional to phi, and of course delta square of phi. Okay. So, this is the spatial derivatives with respect to phi. You will see a new quantity has been introduced here, which is called Cs square. Cs is nothing but the sound speed, and that is given by the derivatives of the pressure with respect to the density. Now, this equation looks quite difficult to solve, mainly because it has time derivatives as well as spatial derivatives, but remember, since we are working in the linear approximation, we have already ignored the terms which may have been higher order in phi. So, the equation is linear in phi, because we want to study only small perturbations. Now, whenever we deal with linear equations, it often becomes helpful to work in the Fourier space. So, in other words, instead of using functions of positions, you go to the Fourier domain by introducing the Fourier transform, as I have done here. Okay. So, the Fourier transform of phi, which is a function of eta and x, is still call it phi, but now it is a function of eta and k. Okay. Ideally, one would have just written this as phi tilde or something, but since once we move to Fourier space, we will stick to Fourier space, there will not be any confusion regarding this phi and that phi. Okay. So, we will just use the same notation. Now, this k, as you can see, has dimensions of 1 over length scale. Okay. So, k dot x has to be dimensionless. So, k should pick up dimension of 1 by x. Now, studying the Fourier transforms as a function of k actually allows you to study various quantities at different scales. For example, if you study this quantity for small values of k, that would allow you to understand the large scale behavior of this potential phi, and vice versa. Large k would give you the small scale behavior of the same quantity. Now, if we go back to the previous equation, what will happen is the derivative with respect to the position coordinate x will be replaced by a multiplication by a factor I times k, which is very easy to show from the definition of the Fourier transform. Now, the evolution of this potential now in Fourier space is given by almost the same equation, except you will see there was this del square term that has been replaced by a term containing k square. You can see it here. Now, this equation, as you can see, it has a second derivative of the conformal time. Then there is this term which is proportional to the first derivative, and that is essentially driven by the expansion. Okay. This a prime by a denotes the expansion of the universe. So, that looks like a damping term. Okay. If this term was not there, it would be easier to grow this phi as a function of time. And then there is this complicated term which is proportional to phi. Out of that, look at this term, this looks like a harmonic oscillator term with a frequency given by Cs time k. So, this is acting like a restoring force. Recall, where did this term come from? This term came from the previous expression which has a del square, and that is essentially coming from the pressure. Okay. That is also easy to understand because there is a Cs square sitting here, which also is determined by the pressure. So, the pressure acts like a restoring force on the potential. Okay. So, you can also think of it as some kind of a effective spring. Okay. So, whenever there are pressure, you will see behavior which are similar to oscillations. This expression holds for any fluid, okay, be it radiation, be it non-relativistic matter, whatever you can think of. Let us now concentrate on radiation perturbations, because radiation perturbations are the ones which are important for studying the cosmic microwave background anisotropies. Now, in this case, the potential will evolve as this is just the previous equation, now specialized to the case where we are working with radiation and also a radiation dominated universe. Remember, for radiation we will put Cs square equal to 1 by 3. In other words, the sound speed will be just 1 by square root 3 times the speed of light, of course, the c, which is 1. So, it is not appearing explicitly in any of the expressions. With appropriate initial conditions, you can work out the solution for this equation, and the solution will look like this. Phi will be 3 times the initial value of the parameter, the initial value of the quantity at eta equal to say 0, and then you have terms like sine and then negative of some factor times cos. Okay. Thus, the evolution of the potential shows oscillatory behavior. Okay. The sine and cos will oscillate, but their amplitudes will keep on decreasing because of this factor sitting here. This is not surprising because this equation has lot of similarities with respect to the harmonic oscillator problem. Okay. And as we also said that this term behaves like the restoring force term, or and this acts as a frequency, and you can see the same thing happens here, k by root 3 appears as if it is the frequency of the oscillator. Okay. So, this oscillatory behavior, again let me remind you, it arises because there is a restoring force which is coming from pressure. On the other hand, there is a driving force which is just gravity. Okay. Now, that was the potential. You can ask what would be the evolution equation for the perturbations, for example, in the radiation density or the temperature or whatever, some observable. Now, the perturbations in the density field are usually described by a dimensionless quantity, let us call it delta. Delta is nothing but the density divided by the average smooth density minus 1. Okay. This is the definition of a quantity which we will call density contrast. Okay. So, you can see if the universe is smooth all over, then this rho will be rho bar at all places, and so this density contrast will be 0. So, any non-zero density contrast tells you about the perturbations, and in the linear limit this density contrast is always much less than 1. Okay. So, you can ignore terms which are like delta square, delta cube and higher order. Of course, its Fourier transform will be denoted by delta, which is a function of t and k, or eta and k, it depends on which time coordinate you are using. For radiation, we will write the density contrast as delta subscript r. Similarly, you can write the delta for matter or any other density field you are interested in. Since the density of black body radiation is proportional to temperature to the power 4, you can also write the dimensionless temperature perturbation as this delta T over T, and that would turn out to be just 4 times the density contrast in radiation. Okay. So, you can either study the temperature perturbations or the perturbations in the radiation density field, and both are very closely related to each other. If for example, you are interested at small scales, when I say small scales, they are kind of much smaller than the horizon, let us say. You can show that the density is related to the gravitational potential by the conventional Poisson equation, and that is nothing but del square of phi being driven by the density contrast delta r, and whatever is sitting outside comes from the evolution of the background solution, okay, how the background density evolves. In Fourier space, this becomes much simpler because this del square, the derivative, is replaced by appropriate k square, and you can show that the delta r and phi in Fourier space are related by this equation. Now, we have already solved for the phi which has oscillatory behavior. So, then the radiation perturbations delta r or the temperature perturbations, they too will show oscillatory behavior. So, this again this arises because of this competition between gravity, which is trying to make the perturbations collapse, and the pressure which is acting like a spring and holding that. Okay. Now, the CMBR anisotropies measure the temperature fluctuations which are just proportional to the density contrast. So, given that we know the solutions which are oscillatory, we can work out how they will look like. They will oscillate, they will go up and down, and we can work out, for example, the positions of the extrema. So, you can go back to the solution in the previous slide, see where the extrema will occur, and you can show that they will occur for a given eta, they will occur at values of k given by this, where n takes values 1, 2, 3 and so on. Remember, this root 3 is arising because of the speed of sound. If we are working in the last scattering surface, because that is where the temperature anisotropies are observed, we have to put the conformal time corresponding to the last scattering surface. Now, when we observe CMB anisotropies, the basic observable is the temperature field along different directions. This, for example, is something which WMAP had observed. You will get a similar picture, for example, for Planck. So, you can see these are different directions along the sky, and each point has a temperature, and the value of temperature is different at different directions. They are very close to 2.73, but there are departures of the order of 1 part in 10 to the 5. So, some parts are colder, some parts are hotter, okay. But effectively you are measuring the temperature field as a function of direction. I have called the direction n hat. You can think of this as theta phi on the sky, the two angles. Now, as we said, it is easier to work in terms of Fourier components. Now, the equivalent of Fourier components in a two-dimensional sphere surface of the sky are these multipole moments, where you expand in terms of the spherical harmonics. Okay. So, you take the theta which is a function of this angle in the sky, multiply by the appropriate spherical harmonics, integrate over all solid angles, all theta and phi. What you get are the multipole moments which are functions of L and M. You can work out what is known as the power spectrum, that is nothing but some kind of mod square of these theta LMs. Okay. The formal definition looks like this, where the angular brackets denote what we call the ensemble average. So, as if you are averaging over many skies, but effectively you will be taking this quantity and averaging over the sky and will calculate this power spectrum called CL. So, these are the angular power spectrum, and this is something, as you can understand, which is directly observable. Often CL is scaled by the average temperature, that 2.73 degree Kelvin. So, CL in that case will have units of temperature square, Kelvin square or millikelvin square or microkelvin square, whatever. Okay. Now, this L has let us try to understand its significance. Remember, for Fourier transform we saw that K has is actually measuring inverse of length scale. So, in the with the same analogy, L is actually will be measuring the inverse of angular scales, okay, angulars of what theta phi, the angles in the sky. Now, we also know that angular scales and length scales are related by a relation like the angular scale is length scale divided by distance. For example, it can be the angular diameter distance, if you remember our previous lectures. So, if we write that, you can see that L and K gets related by something like this. L will be K times the distance to the object where you are measuring, or to the redshift you are measuring. Okay. In this case, this would be the distance to the last scattering surface. Great. So, we have already seen that the temperature fluctuations will show peaks at K peak. Since we are observing them at the last scattering surface, this will end up being peaks at typical values of L, or some values of L, which is given by K times the distance to the last scattering surface. Remember, distance is just conformal time in this case. So, the conformal time to last scattering surface is just the difference between the conformal time today and the conformal time at that epoch, and if I substitute for the value of K peak, it turns out to be an expression like this. So, these are the values of L, where CL will show peaks. These are known as acoustic peaks. So, let us discuss that. So, the CL for temperature fluctuations will show peak at this, which can be approximated as a ratio of eta naught, today's conformal time, divided by the conformal time at the last scattering surface. This is because the conformal time today is much larger than the conformal time at the last scattering surface. Now, I mean, everything here is known. So, one can calculate the value of L where the first peak occurs, and you can show that the value would turn out to be of the order of 200. Okay. I will leave you to work out what is the corresponding angular scale for. Okay. Actually, this value is sensitive to the curvature of the space, because that will affect the distance to the last scattering surface. To be very precise, it will affect the relation between the angular scale and the linear scale or the length scale. Again, this is something when we were discussing the angular diameter distance, we talked about these things in slightly more details. These peaks arise because of gravity being opposed by pressure gradients, which basically is setting up this sound or acoustic waves. So, these peaks are called acoustic waves. So, if one plots the CL, which has been plotted here, this is CL as a function of L, you can see it has many features, but one of the features is this peak like structure. There is a peak here, it goes down, again picks up, there is a peak here, peak, and there are a lot of peaks. Okay. And you can see the first peak is arising somewhere around L of 200, this is for the standard cosmological model. Okay. And then there is a second peak and so on, and these positions of the peaks are more or less determined by a relation like this. Okay. So, you can see you are already starting to quantitatively explain the behavior of CMBR anisotropies, at least the statistics of them. There are many other aspects of this plot. For example, if you take the perturbation solution at very large scales means I have to take very small k. So, you put k going to 0, you will find that phi is given by the value of phi at eta equal to 0 for the same k. So, this basically tells you that the multipoles at small l are actually measuring the initial conditions. This phi at eta equal to 0 is your initial conditions, and that is what is written here. So, this part is essentially driven by the initial conditions. This is a very good probe of the initial conditions of the fluctuations. Okay. In fact, there are many ways of specifying the initial conditions. A most convenient way is to specify in terms of what we call the primordial power spectrum. So, the primordial power spectrum of the potential is nothing but something which is proportional to the mod square of the potential perturbations, okay, at the initial time. Usually the primordial power spectrum is assumed to be of the scale free form like this. So, you say k cube p of phi is proportional to k to the power n minus 1. This type of behavior is often also predicted by inflationary models, which give you a paradigm for generating perturbations through quantum effects. If the spectrum is scale invariant, then you have n equals to 1, then you have the same power at all scales. The matter power spectrum is written as p of m, which is proportional to k to the 4 p phi. This comes basically from the Poisson equation. If you remember, the delta, the density contrast is related to the potential through a factor of k square. Okay. So, that is how you pick up. So, the power spectrum will pick up a factor of k 4, and then you can show that the power spectrum of density fluctuations or matter fluctuations will go as k to the n. Of course, there is a proportionality factor. So, there will be a normalization, and that normalization is also fixed by comparing with observations. Okay. There are various other effects which also characterize these anisotropies or the behavior of this CL as a function of multipole L. So, let us just talk about a few of them. For example, there is something called Sachs-Wolf effect at very large scales, that is very large scales means very small values of L. The temperature fluctuations are related to the gravitational potential at the last scattering surface. In the sense, overdense regions correspond to cold spots in the sky, and that has a prediction for how the CL will look like, and that is imprinted somewhere here at large values of L. Okay. Then there is a concept of baryon loading. So, in the last the equations which we talked about, actually we never incorporated the matter there. In fact, there is a presence of baryons which interact very closely with photons, with radiation before recombination, before the last scattering surface, because they are constantly getting scattered off via Thomson scattering. Okay. So, this presence of baryons, this will provide some extra inertia, and that will essentially reduce the sound speed, okay, by some factor. This will shift the locations of the peak by some amount and also will change the amplitude. Okay. So, baryon loading which starts affecting things somewhere here. Okay. Then there are damping effects or dissipation which occurs at very small scales at large L. At small scales, this baryon photon fluid, remember these baryons and photons, the electrons and the radiation are constantly scattering off each other, interacting very closely. So, they act as one fluid, baryon photon fluid. However, it is not a perfect fluid, but it shows imperfections like viscosity and so on. So, the effect of such imperfections is to damp the acoustic oscillations, and they are prominent at rather small scale. So, you can see the CLs actually die down quite fast as you go beyond L's of thousands or so. Now, the importance of studying CMBR anisotropies or these CLs is that these CLs are quite sensitive to cosmological parameters, and that has been shown here. So, these are plots of CL versus L, and in each panel only one of the cosmological parameters are varied and the corresponding curves plotted. For example, in this case one studies the effect of varying the curvature parameter or omega total. Okay, remember omega total 1 means flat universe, and omega total less than 0 will give you a universe which has less matter. So, it is an open universe. Okay. So, and different colors correspond to different values of omega total. So, you can see depending on whether there is curvature or not, the location of the first peak changes drastically. This is something I was discussing just a few slides back. The location is determined by the angular diameter distance, and that actually depends on whether you are living in a flat universe or a curved universe. So, if one can constrain the location of the peak quite accurately from CMBR observations, one immediately gets a constraint on what could be the range of allowed values of omega total or the curvature parameter. You can see the dependence on dark energy. Now, dark energy, the dependence is relatively weak. What happens to baryon? So, this is the dependence on the value of omega b multiplied by Hs square. You can see if I change omega b, the location of the first peak does not change that much, there is a small change maybe, but the amplitude changes drastically. Okay. So, again if one can measure the amplitude of the first peak, that gives you an handle over omega b. But then there are complications because the amplitude of the first peak depends on the matter density as well, omega m, okay, which is shown in this panel. So, then one has to go beyond first peak and do various things like the relative ratios of the first and the second peaks and so on. So, just to summarize, you can see this anisotropies depend very crucially on the cosmological parameters, and that is why the CMBR observations have been very useful for constraining cosmology, just because the dependence is quite strong, and CMBR observations have become more and more precise and accurate in recent times. There are also some secondaries. These have to do with the fact that the CMBR has left the last scattering surface and free streaming towards us, but in between that the photons may interact and interact in different ways. Again, there are various things which one can talk about. I will talk about only a few of them. For example, there is something called the integrated Sachs-Wolf effect. What happens is, as the photon is coming towards us, it is passing through the gravitational field of matter of the universe. So, what happens is there could be some potential wells, there could be regions where the gravity is quite strong, maybe a cluster of galaxy has been formed, a huge structure is there. So, there is a potential well. So, what happens is the photon will enter this potential well in with certain energy. As it is falling down the potential well, it will gain energy. So, it will be blue shifted. However, when it is coming out of the potential well, it becomes red shifted because it loses energy. If during this whole process the potential well does not change, then the loss and the gain will cancel each other. So, in effect you will not see anything at the end. However, if the potential changes when the during the photon going in and coming out, what will happen is the loss in energy and the gain in energy could be different, and there could be some net effect which one can see, and that is known as the integrated Sachs-Wolf effect. And this would happen along the line of sight. As the photon is travelling, whenever it encounters a potential, it will suffer this thing because of the changing potentials, and that will show up in the CMB observations. Remember, this is secondaries because this is happening because of something not in the large scattering surface, but between large scattering surface and us. There are other secondary effects like the Sunyaev-Zeldovich effect, where a microwave CMBR photon comes and passes through a gas which is hot, sitting in again galaxy clusters. This hot gas has energetic electrons, and if the photons scatter of these energetic electrons, they may be gaining energy. Okay. So, they get blue shifted, and then when we observe them, we will observe a distorted view of the CMBR universe. Okay. This is known as Sunyaev-Zeldovich effect. There are more details related to Sunyaev-Zeldovich effect, which I am not going into. Then there are other secondaries which have to do with suppression of the amplitude of the CLs. This happens if the universe gets ionized at late times. So, then what happens is the CMBR photon starts getting scattered again of the free electrons produced because of this ionization, that will lead to suppression of the inhomogeneities. This ionization is a effect due to what is known as cosmic reionization, where the universe gets ionized once more. So, there are a lot of free electrons to interact with, giving rise to this suppression in the amplitude. Till now we have been talking about the temperature anisotropies, the variation of the temperature across the sky, but there are other effects, other observables of CMB which have to do with the polarization. So, the CMB radiation is polarized, and this polarization arises due to the quadrupole, the existing quadrupole anisotropies in the radiation field, and of course, the Thomson scattering of free electrons. For example, imagine an electron here and it is bombarded by CMBR photons from all directions. So, let us consider two orthogonal directions, and let us say we are only looking at scattering at 90 degrees. Okay. So, this wave comes, which let us take it to be unpolarized to start with. So, it has two polarizations and both the directions have equal amplitude. It gets scattered by 90 degree. What happens is, if that happens, the polarization along the direction of travel then gets suppressed, it is not present anymore. So, you end up with a light which is polarized along this direction. So, only this blue survives. Okay. The blue along this direction has vanished because the polarization has to be orthogonal to the direction of propagation. Imagine another light coming from here. So, in this case, this after scattering, this polarization will vanish. So, you end up with a polarization like this, okay, the red one. Now, if the intensities of the electromagnetic wave from this direction and these directions are same, then what will happen is these two polarization amplitudes will also be the same. So, the net light will still be unpolarized. However, if there is a quadrupole anisotropy, then what happens is the intensity along this direction and this direction will be different, and that gives rise to a net polarization, which in principle can be observed. The polarization signal strength unfortunately is much smaller than the temperature in terms of the anisotropies. So, what has been plotted here are the CLs again normalized in some way versus L. This is the temperature CL. Okay. So, what we do, why I would have done is I would have taken the temperature anisotropies, decomposed into the multipoles and then taken the mod square basically. So, we call it temperature CL, and that we have seen that shows this peak structure and so on, the acoustic peaks and so on. So, this is how it will look like, and the typical amplitudes in terms of microkelvins are few tenths of microkelvins. Okay. Remember, they are 1 part in 10 to the 5. So, if you do 10 to the minus 5 of 3 Kelvin, you will end up somewhere here. Okay. So, this is what we expect. Great. Now, suppose we do the same thing with polarization. So, there are again two types of polarizations. This is called something called the E mode polarization and something called the B mode polarization. This is how this is actually based on how the vectors are oriented. So, suppose I take the E mode polarization and play the same game, calculate E. Basically, I do the correlation of E modes with themselves. Then what I will get is a signal which will look like this green curve. You can see this is way smaller than the temperature signal. Okay. There is something in between where what you do is you correlate between the temperature and the E mode correlation. So, that will be somewhere between these two plots, and this is here. Okay. So, here you are talking about signals of the order of microkelvin, whereas this was few tenths of microkelvin. There is another type of polarization, the B mode, and this B mode is essentially sourced by the gravitational waves, but again their strength is way smaller than even the E mode signal. So, they are like just 0.1 of microkelvin and so on. So, these are much more difficult to observe. So, till now we do not have any direct observational evidence for this B mode signal. Once we have that, that will be path breaking, in the sense we would have actually detected primordial gravitational waves. So, that is why there are a lot of experiments which are trying to probe this, detect this. Okay. The B mode signal can arise for from other effects as well. For example, secondary effect which have to do with lensing of the CMBR signal. So, imagine there is a CMBR sky and we are observing here, but the photons are passing through all this cosmic wave, the large scale structure, okay, all these potentials, and as the photons pass through this gravitational potentials, the photons bend. Okay. This is a prediction of general relativity, that light will bend when it passes through a potential. Okay. So, this is called lensing. So, the CMBR photons will get lensed, and one can show that this lensing will give rise to an additional signal which will show as B mode polarization, and that is again something which is an interesting case to study. Okay. Now, we are at a point where we can talk about precision cosmology using CMBR. So, what happens was is that you take these CLs not only for the temperature, but also polarization, and then you try to fit a model of cosmology with various free parameters. The free parameters which we talked about, like the baryon density, the density in dark matter, the dark energy, maybe the curvature, the value of the Hubble parameter. Okay. And on top of that, there are other quantities like the power law of the primordial spectrum, which I wrote it as n, maybe the normalization of the primordial spectrum and so on. All these informations are actually hidden in the CMBR signal. So, one would then like to constrain these parameters by matching the theoretical model with the CMBR observations. This has given rise to what we call the era of precision cosmology, because now the cosmological parameters are being measured to a very high degree of accuracy. What I have shown here are the Planck results, okay, which have come out last year basically. This shows the parameters, then various columns are the way you have analyzed the data. For example, this one would say that you would have used the temperature data and E mode polarization data, but only the low L values, the large scale E mode polarization data, and so on. And then you go on adding various other things. Here for example, they would have used temperature, the temperature E mode cross correlation, and then EE, the E mode cross correlation plus this low E data and so on. Okay. Then here they have added the signal from this lensing, which I talked about in the last slide. Here they have added something more, which have to do with the baryon acoustic oscillations. This is something I will come to in the next lecture. So, this is basically how much data you are going to use to constrain the parameters, and now you can start seeing the constraints. So, let me try to highlight a few things. For example, you can ask what is the constraint on omega b times Hs square. So, you can see the best fit value is somewhere around 0.022, but look at the error bars. Error bars are now 0.002 after the decimal. Okay. So, you can see how precise the measurements have become. So, if you come down, you will see various parameters which we have discussed. For example, the value of H naught. Till now I have been saying that H naught is of the order of 70 from recent observations, and you can see what the values are. It slightly depends on what kind of data sets you are going to use, but the error bars are of the order of 0.4. Okay. So, if you for example use this data set, we are talking about a H naught which is 67.66 plus minus 0.42. Okay. So, it is not really 70, it is less than 70 to a very high degree of precision. Omega lambda turns out to be somewhere around 69%, but again look at the error bars, very precise. Omega matter turns out to be just 1 minus of this. Omega matter contains both omega baryon and omega dark matter. Okay. Sigma 8 is nothing but something to do with the normalization of the power spectrum, which is quite crucial for studying structure formation. Then comes the age. Age is something which is given everything else, one can determine the age. Age now we are talking about is somewhere in the range 14 gigayears. Okay. In fact, it is 13.787, and then the error bars are plus minus 0.02 if we believe this data set. Okay. So, you can see again the precision with which one is measuring various things. The other thing of interest is this slope n, which measures the slope of the primordial power spectrum. Remember, we model the primordial power spectrum as k to the power n. If we want it to be scale invariant, then n should be 1. What is the measured value? It is 0.966 plus minus 0.00, let us say 0.004. So, if you work out, you can see that it is not 1, it is actually less than 1. Even within error bars. Okay. So, even if I magnify the error bars by 3 or so, which we call the 3 sigma limits, it is not going to hit 1. So, n equals to 1 at present is ruled out. Okay. So, the power spectrum is not scale invariant, but it has a slope and it is slightly less than 1. Okay. There is another parameter called tau. This has to do with the cosmic reionization. So, it tells you when the universe got reionized again. Okay. So, the universe got neutral at redshifts of somewhere around 1000 or 1100. This is during the recombination and the last scattering surface. After that, it got reionized again, and when it got reionized, how long was the reionization is encoded in this parameter. If you want to convert this parameter into something which you understand, you have to go and look at this quantity, which is called Z reionization. This talks about the redshift at which the universe got reionized, typically the median redshift, and you can see we are talking about redshift somewhere around 7.5 to 8, okay, with some error bar of course. So, this is not as precise as other quantities, but this is where it is. Okay. So, we are talking about reionization at 8. Okay. So, there are many other information which are hidden here, and in fact, this table actually runs much longer, which I have not shown you here, but there are lot of information which is hidden. So, just to summarize, CMBR itself tells a lot about Big Bang cosmology, but when you go to anisotropies, it is actually giving you severe constraints on the values of the cosmological parameters. Now, we are living in a age where we can do precision cosmology, we can measure the cosmological parameters to a very high degree of precision, and this table actually tries to give you some idea about how precise these measurements are. This is again a good point to stop, and in my last lecture, the 6th lecture, I will be talking about a bit more on structure formation galaxies and other large scale structures, and how they help in understanding cosmology and our universe. Thank you.